Welcome to Linkafidi's Deep Dive. We're here to break down complex research, pulling out the key insights so you can stay ahead. Like us and subscribe to get more podcasts like this. Today, we're diving into a really significant paper, especially for those of you working in medical AI applications. It's called Advancing Conversational Diagnostic AI with Multimodal Reasoning, and it's from Google DeepMind. Our goal here is a proper scientific discussion, going through it almost page by page, focusing on what's relevant for data scientists like you.
Absolutely. It's a dense paper, no doubt, but packed with important stuff. We'll pull out the main contributions they use, what the results actually mean, all using the kind of technical language you'd expect. The authors, Saab John Freiberg, PCJ Alan Carthy, and Tano are really pushing things forward with conversational AI in a clinical setting.
Right? So, let's jump in. The paper starts by setting the scene, right? Acknowledging the progress with LLM-based conversational AI, how they're showing some promise in text-based clinical chats, things like triage. But, as they point out, it's mostly been text, hasn't it?
And exact the gap. While these LMMs are frankly amazing with text, real medical diagnosis involves way more. Doctors are constantly looking at skin photos, ECGs, lab reports, all sorts of things. So the big question this paper tackles is, how do we get AI to handle all that multimodal data within a conversation?
And that's where multimodal AMIE comes in. They've enhanced AMIE to handle this, building on Gemini 2.0 Flash. The core seems to be this novel state-aware framework. What's the thinking behind that architecture?
Yeah, the state-aware framework is really central. Instead of just reacting to the last thing said, it lets AMIE dynamically track the conversation state. It uses intermediate outputs from model, basically the AI's current best guess about the patient's state, its diagnostic ideas, and how uncertain it is. This lets it manage the whole diagnostic process much more deliberately. It's key.
Okay. And to test this, they didn't just run simulations. They used a pretty rigorous method, a randomized blinded human EV evaluation like a virtual OSCE. Why is that particular method so important here?
Well, the OSCE objective structured clinical examination is kind of the gold standard in medical training for testing practical skills in a standardized way. By using trained actors as patients in realistic scenarios, you can directly compare skills like taking a history, interpreting data, in this case skin photos, ECGs, documents uploaded in a chat, diagnostic reasoning, communication, all of it. Adapting it to this remote text chat format with multi-total uploads gives a really strong benchmark for comparing AMIE against actual primary care physicians or PCPs.
And the results from this virtual OSCE, what was the main takeaway?
Pretty striking, actually. The headline is that AMIE generally performed as well as or even better than the PCPs. Of course, a whole range of important clinical measures. We're talking about things like the accuracy of the top 3 diagnoses considering all the multimodal info, the quality of the management plan suggesting the right level of escalation, interpreting images without hallucinating, even things like whether the patient actor felt AMIE was honest, trustworthy, empathetic, and if they'd be happy to consult it again.
That's quite a list. Okay, let's dig into the details page by page. Starting with page 3, outlining the key contributions. The first one is multimodal state-aware reasoning at inference for our audience. What's the core innovation there architecturally speaking?
Right? The main thing is this state-aware dialogue phase transition framework. That's figure 2 in the paper. It's different from just trying to get everything right with complex prompts. This framework explicitly manages the flow. It uses Gemini 2.0 Flash not just for understanding language, but also to generate these intermediate outputs that capture the evolving patient state symptoms, current diagnostic hypotheses, uncertainty levels. This lets the system actively decide what to do next. It's not just reactive.
So, it's more like it's managing the diagnostic journey, rather than just answering questions.
Precisely. It allows AE to figure out strategically when to ask for a particular piece of multimodal data, like, okay, based on these symptoms, I really need a skin photo now, or maybe an ECG or a lab report. And once it gets that data and interprets it, the findings feed directly back into the reasoning, refining the diagnosis, guiding the next questions. It really tries to mimic how an experienced clinician thinks in a telehealth context.
Okay, the second contribution on page 3 is the simulation environment for dialogue evaluation shown in figure 3. Why bother building a whole simulation framework?
That's super important for development and testing. It gives you a way to rapidly iterate and evaluate things automatically at scale. Their framework has 3 parts. First, generating realistic patient scenarios. They don't just make stuff up. They use real medical image data sets. Scene for skin, PTBXL for ECGs. Clinical QA for documents, and end them with plausible clinical details using Gemini and web search. So, the scenarios are grounded.
Right? Data-driven scenarios. What about the other 2 parts?
Second part is the dialogue simulation itself. You have the AI agent programmed to be empathetic and clinically accurate, interacting turn by turn with a patient agent who sticks to the script from the generated scenario. They exchange text, upload images just like a real chat. And the third part is the auto-rider. This is another AI agent that automatically scores the simulated conversation against clinical criteria, diagnostic accuracy. Did it gather enough info? Was the management plan sensible? Did it hallucinate anything? This gives them quantitative metrics fast.
Makes sense. The third contribution is the expert evaluation via the multimodal OSCE. We touched on it, but what's scientifically notable about how they ran this evaluation?
The key here is the rigorous human validation in a safety-critical area. They ran this remote OSCE with 105 different case scenarios. They used validated patient actors who had synchronous chats blinded, so they didn't know if it was AI or a doctor using an interface that allowed actual multimodal uploads. This setup provides really rich data. Both quantitative scores and qualitative feedback on how the system performs in a situation that's very close to a real telehealth consult.
And the fourth contribution just summarizes the head-to-head comparison between AMIE and the PCPs in that OSCE. What was the bottom line quantitatively?
The main finding was that AMIE's ability to handle and interpret that multimodal data during the conversation was statistically speaking either better than or equivalent to the primary care physicians in the study. And importantly, AMIE actually scored higher on average for things like diagnostic accuracy, the reasoning behind the management plan, and even perceives empathy. There's pretty strong evidence for this multimodal state-aware approach.
Okay, let's move to page 5, the approach section. They reiterate the goal, adding multimodal perception beyond just text. And again, it centers on that state-aware dialogue phase transition framework. Can you walk us through the main phases and how it shifts between them?
Yes, page 5 fleshes out the method. It revolves around that state-aware framework using Gemini 2.0 Flash. It structures the conversation into 3 main phases: history-taking, then diagnosis and management, and finally follow-up. But it's not rigid. The crucial part is that moving between phases and deciding what to do within a phase is driven by those intermediate model outputs. The AI's assessment of the patient state, its current hypothesis, its uncertainty level. It adapts dynamically based on this internal state.
And the page mentions the 2 evaluation tracks again, the OSCE expert evaluation and the automated pipeline section 2.2. Let's quickly revisit the automated one. What were its main jobs?
Right, the automated pipeline was complementary. Its main jobs were first the basic perception skills of the underlying Gemini model on isolated artifacts. Can it actually see the relevant features in a skin photo or ECG? And second, to use the simulated dialogues and the auto-rater to quantify how much the state-aware framework in the conversational context actually improved diagnostic performance compared to simpler approaches. It provides scalable objective metrics.
Got it. Now section 2.1 on page 5, multimodal state-aware reasoning. They talk about how real clinical dialogues are structured but also flexible. What's the key insight about how clinicians operate?
The insight is that good clinicians have a dynamic process. They gather information, form initial ideas, ask targeted questions which might include asking for specific tests or images, interpret the results, update their assessment, and eventually propose a plan. It's adaptive. The questions they ask, the data they seek. It all depends on their working diagnosis and how confident they are. You don't just follow a checklist blindly.
And the paper argues that having this explicit state-aware system layered on the LLM is better than just relying on clever prompting, especially for something high-stakes like diagnosis. What are the claimed advantages?
They hypothesize several key advantages. First, more control over the dialogue flow, making sure critical steps aren't missed. Second, better tracking of the diagnostic state and uncertainty, leading to more informed choices by the AI. Third, a more deliberate integration of the multimodal input. And ultimately, they argue in their ablation studies in section 4.2 seem to back this up. It leads to more reliable, higher quality clinical reasoning than just trying to steer a base LLM with prompts alone.
So this state-aware framework, managing the process through history-taking diagnosis management and follow-up, is really the engine here. And the transitions are driven by these internal model outputs shown in Figure 2. How does that internal state actually guide the conversation?
Think of those intermediate outputs, the patient state, the hypothesis as a control signal. They tell the framework, okay, we still have major gaps, keep asking history questions or confidence is high enough. Let's move to presenting a diagnosis or let's focus on answering follow-up questions now.
And within a phase, these signals dictate the specific actions, like generate a question focused on symptom duration or request an ECG because of these reported palpitations. It ensures the dialogue is driven by the AI's evolving understanding and diagnostic goals, incorporating everything learned so far, text, docs. It aims to mimic that adaptive clinical reasoning. Let's go to page 6. Delving into phase 1, history taking first step. Patient profile initialization. What gets stored here and how does it evolve?
Right. The patient profile is basically a structured summary of everything known about the patient. It starts with whatever info is available initially, then gets updated continuously. It tracks the chief complaint, history of the illness, demographics, symptoms, past medical history, family history, social factors, travel, meds, all the standard stuff. Critically, it also keeps a running list of knowledge gaps, things AMIE realizes it still needs to find out. So it starts potentially quite sparse and gets filled in as the conversation goes on.
Step 2 in history-taking evolving differential diagnosis, DDX generation. So, AMIE starts thinking about possibilities quite early.
Yeah, it does. Once it has some initial info, it starts generating an internal list of potential diagnoses. But, and this is important, it doesn't show this list to the patient initially. Like the AI's internal scratch pad, it's working hypothesis, and this list gets updated regularly as more information comes in. How often it updates is actually something that can configure.
Step 3 is the continuation decision. This sounds like a key junction deciding whether to keep asking questions or move towards a diagnosis. How does it make that call?
There's a specific decision module for this. It uses Gemini 2.0 Flash to look at the conversation so far and the current internal DDX list. It essentially asks, do we have enough information to make a reasonably informed guess about the diagnosis? If there are still big gaps or the uncertainty is too high according to its criteria, it decides to stay in the history-taking phase.
And if it does decide to continue history-taking, we get to step 4, targeted question and multimodal data request generation. This is where it asks for photos or ECGs, right? What's the logic?
Exactly. If more info is needed, it doesn't just ask random questions. It generates questions specifically aimed at filling those identified knowledge gaps or reducing certainty in its DDX. And this is where the multimodal part is crucial. It's designed to recognize situations where seeing something would be really helpful. Patient describes a weird rash. Okay, can you upload a photo? Chest pain, maybe an ECG would be useful here.
Really?
It even prompts for specific details about the uploaded artifact, like asking about the lesion shape, color distribution for skin, or rhythm, waveforms for an ECG. This ensures it gets the key features needed for its reasoning. Then it presents that question or request to the patient. Okay, moving on to page 7 in phase 2. Delivered diagnosis and management. First step here is internal DDX refinement. How does it update its list now? So based on everything gathered in phase 1, the detailed history plus the interpreted findings from any uploaded images or documents, AMIE reassesses its internal differential diagnosis. Probabilities might get updated. Conditions that look more likely based on the combined evidence move up the list, while less likely ones might move down or be dropped entirely.
Then in step 2 is patient-facing DDX generation and delivery. How does it actually tell the patient what it thinks is going on without being confusing?
This is key for communication. It generates a concise summary of its top few diagnoses, usually the most likely one, plus maybe 2 or 3 other strong possibilities. The emphasis is on using clear, simple language, avoiding jargon. It doesn't want to overwhelm the patient. It also briefly explains why it thinks the leading diagnosis is most likely, linking it back to specific things the patient said or findings from the images.
Step 3 is uncertainty expression. So it's designed to be upfront if it's not completely sure. Why is that built in?
Transparency is really important for trust. If AMIE still has significant diagnostic uncertainty after reviewing everything, it's programmed to say so. It might say something like, based on everything, X is the most likely possibility, but we also need to keep Y and Z in mind. Acknowledging uncertainty manages expectations and can naturally lead into why further tests might be needed in the management plan, which brings us to step 4, management plan formulation. How does it decide what to recommend? After presenting the possible diagnosis, AMIE develops a management plan. This plan is based on the whole clinical picture. The history, the profile, the DDX is presented. It includes recommendations, things like further tests to confirm the diagnosis or rule out alternate options for treatments or lifestyle advice. And finally, Step 5 in Phase 2 is management plan delivery. How is this presented and what signals the move to the next phase? AI presents the plan, but often not all at once. It might deliver it over several conversational turns, allowing the patient to ask questions, express concerns, and really understand the recommendations. Once AMIE has presented both the refined differential diagnosis and the management plan, that marks the transition to Phase 3, which is all about addressing any remaining questions.
Okay, page 8. Phase 3, answer follow-up questions. Seems straightforward, but crucial for wrapping things up. What happens here?
Right, the main goal is clarity and closure. First, the patient profile might get updated if new relevant info comes up during follow-up questions, but that's optional. The core is Step 2, communicating the plan clearly and answering all patient questions. AMIE tries to ensure the patient understands the what and why of the plan. It might even refer back to the images or documents if that helps explain things. All its responses are guided by the full context, history, profile, DDX plan.
And Step 3 is dialogue termination. When does it decide the chat is over? Basically, when the patient seems satisfied, all questions have been addressed, the plan is clear, and the conversation reaches a natural endpoint. But importantly, page 8 mentions something that happens after the chat ends, generating a structured post-questionnaire. What's that for?
Yeah, this is an automated step once the conversation terminates. AM generates the structured summary based on the entire interaction, TEDG's interpretations, its final internal state profile DVX plan. It's specifically prompted to finalize its differential diagnosis into a ranked list, and critically it formulates a detailed management plan grounding it with web searches for current guidelines. This includes specific investigations, actions, escalation level like needs video call or see doctor in person, with justification and follow-up details. Why? It's a neat summary of the AI's final conclusions.
Let's look at page 9, figure 3. It's the overview of the multimodal dialogue simulation and evaluation framework. We've covered the pieces, but what does it visually emphasize for a data scientist looking at this?
Figure 3 really ties together their automated pipeline. Step 1, patient scenario generation, clearly shows they're using real datasets PTB Excel, scenes plus wedge to create grounded, detailed patient profiles and scenarios. Step 2, dialogue simulation highlights the actual interaction. The AMIE doctor agent and the patient agent chatting with that crucial multimodal artifact upload capability. And Step 3, auto-rating visually shows how another agent assesses the simulated dialogue using predefined criteria like management appropriateness, info gathering. You can see the Likert scale example and checking for hallucinations against the ground truth. For a data scientist, it shows a structured, data-driven way to build and test these kinds of systems. Moving to page 10, diving deeper into Step 1, synthetic patient scenarios. How did they create these for dermatology specifically? For dermatology, they had a bit of an advantage because they used the SCI and PAY-DD20 datasets. These datasets already came with a lot of rich patient info, age, sex, symptoms, skin tone, medical history, social history. So for the skin condition scenarios, they didn't need to synthetically generate much patient background. The data was already there, making the scenarios quite detailed from the start.
But for cardiology, using the PTB SXL dataset, they needed to add more context, right? How do they do that?
Exactly. PBXL mainly gives you the ECG and basic demographics like age and sex. So they use Gemini 2.0 Flash combined with web search to fill in the blank. They imputed clinically plausible symptoms, social and family history, medical background, and cardiovascular risk factors that would typically go along with the conditions suggested by the ECG. They tried to ground this imputation in real medical knowledge found online to make the cardiology profiles more complete and realistic.
And what about the clinical document scenarios? They were created with clinical partners.
Yes, those were developed collaboratively, focusing on common primary care conditions. They designed realistic-looking but fake documents, blood tests, urine reports, dual analysis, fake consultation notes. The key was these documents contained important clinical clues that needed interpretation, but they didn't just spell out the diagnosis or the management plan. And to add another layer of realism for about half the scenarios, they simulated taking smartphone photos of these documents off a screen, introducing potential image quality issues you might see in telehealth.
Okay, page 11, step 2, turn-by-turn multimodal dialogue generation. The AMIE agent interacts with the patient agent. What are AMIE's core instructions? During these simulations,
In the simulations, the AMIE agent is basically programmed to act like a good telehealth doctor. It's told to be empathetic and clinically accurate. Crucially, it uses that state-aware dialogue framework we discussed to manage the conversation history, diagnosis, follow-up. And its key multimodal ability is to strategically ask for and analyze relevant artifacts like skin images or ECGs based on what the patient agent reports, who in turn is just truthfully following it. Scenario.
Page 12 brings us to step 3, auto rating of simulated dialogues. Let's quickly run through those criteria again. First, differential diagnosis accuracy.
Right, this measures if the correct diagnosis, the ground truth of the scenario, is in AMIE's top 1, 3, or 10 list in the post-questionnaire. It accounts for synonyms. It's a simple yes, no for each dialogue, then average it across all simulations.
Second, gathering information.
This looks at how well AMIE elicited information. Did it ask open-ended questions, listen actively, address concerns, summarize effectively? It's rated on a 5-point Likert scale from very poor to excellent.
And briefly, management plan appropriateness, hallucination, and empathy.
Management plan appropriateness checks if the proposed plan is clinically sound and safe. Investigations, treatment, follow-up, also a 5-point Likert scale. Hallucination is a binary check. Did AMIE make stuff up or state factual inaccuracies? Empathy uses another 5-point scale to assess if the model showed understanding and responsiveness to the patient's emotional state.
And the page mentions this framework is in advance, and Appendix C.3 calibrates the auto rater against human judgment. Why is that calibration step important?
It's crucial validation. It shows that the automated scores generated by the auto rater actually align reasonably well with how human medical experts would rate the same conversations. If the auto rater agrees with experts on which dialogues are better or worse, it gives you confidence that you can use this automated system for large-scale evaluation during development. It makes the whole process much more efficient.
Okay, let's switch gears to page 13, section 3, expert evaluation, multimodal virtual OSCE. This is the big human evaluation part. What were the main goals here?
The expert evaluation was designed to be a really tough, realistic comparison of AE against actual PCPs doing multimodal diagnosis. They extended an existing remote OSCE method specifically to include handling multimodal data. The goal was to assess dialogue quality using metrics from both the patient's perspective, the actor and specialist doctor perspectives, and they developed a new rubric just for evaluating how well multimodal data was used. The OSCE format itself with standardized cases and blinded evaluation makes the comparison robust.
And just quickly remind us what an OSCE is and why it fits here.
Right. An OSCE is a standard practical exam in medicine. Instead of just written tests, candidates rotate through stations with actor patients presenting specific problems. They have to perform tasks, take a history, examine, interpret results, counsel while being scored by examiners using checklists. It fits here because it tests the practical application of clinical skills, which is exactly what you want to evaluate in a diagnostic AI history-taking, interpreting data, including images, docs here, reasoning, communication. The OSCE structure is perfect for assessing those in a standardized way relevant to telehealth.
Page 14 talks about the scenario packs for the OSCE and Table 1. What kind of cases did they create for these 105 scenarios?
They worked with OSCE groups in Canada and India toward these 105 scenarios. They focused on 3 common artifact types in primary care: telehealth, skin photos from smartphones, ECG tracings, and clinical documents. Table 1 gives the breakdown and examples. They use different representations, photos from different angles, screenshots to mimic real-world quality variations. Skin cases came from the scene data set. ECGs from PTB documents were custom-made by the OSCE labs. They included normal cases, too. Critically, these scenarios were designed so you needed both the patient's story and the interpretation of the artifact for a confident diagnosis. They deliberately picked challenging images for skin and ECG and worked with specialists to make sure the text parts complemented the images. Even though they were created after the fact, they tried to make them consistent and clinically plausible.
Page 15 covers the study participants and procedure who took part in this OSCE.
3 groups, 19 board-certified PCPs with a median of 10 years experience, 20 validated patient actors split between in India and Canada trained to play the roles in the scenarios, and 18 specialist physicians, cardiologists, internists from India and North America who acted as the expert evaluators. Each specialist evaluated cases only within their own specialty. The procedure was quite thorough. Each of the 105 scenarios was done twice by each actor, once with a random PCP, once with the IE in a randomized order. That's 200 consultations total. And then each of those consultations was independently evaluated by 3 specialists. That's a lot of evaluation. Page 16 details the evaluation metrics. They used existing rubrics, but also added a new multimodal understanding and handle EMU rubric. What did this new EVU rubric focus on? While many metrics came from established rubrics looking at general consultation quality, diagnosis, managed communication, etc., The MU rubric was new and specifically designed for this study's focus. It zeroed in on how well the consultant AMIE or the PCP dealt with the multimodal data. Did they ask for the right artifacts? Did they interpret them accurately? Did they integrate the findings into their reasoning? How well do they answer patient questions about the images or documents? Figure 4 gives a nice overview of the whole evaluation flow, showing where the MU rubric fits in alongside other patient and specialist ratings.
Page 17 describes the statistical analysis. They used mixed effect models. Why that approach?
Mixed effect models are ideal for this kind of study design. You have multiple consultations nested within scenarios and multiple specialists evaluating each patient. This model lets you separate out the variability due to the specific scenario, treating it as a random effect from if you're interested in the difference between AMIE and PCPs, the fixed effect. It accounts for the fact that some scenarios might just be inherently harder than others. They use specific types of these models for the different kinds of ratings. Ordinal models for Likert scales. Models for binary outcomes like correct diagnosis. They also use statistical tests like chi-squared and Whitney U tests for specific comparisons. It's a robust way to analyze complex nested data and be confident in the significance of the findings.
Okay. Page 18 starts the results section. It mentions two main sets of results. What are they?
First, section 4.1, they present the results from that head-to-head comparison against PCPs in the multimodal OSCE study focusing on diagnostic accuracy, conversation quality, multimodal handling based on the human evaluations. Second, section 4.2, they show findings from their automated evaluation framework. Things like how well the base model perceives medical images and ablation studies showing the impact of their state-aware reasoning system. Together, these give a comprehensive picture.
Let's look at page 19, section 4.1, the OSCE results, starting with diagnostic accuracy. The big claim is it was superior. Figure 5a shows this. What does that graph tell us?
Figure 5a is pretty clear. It plots top accuracy. The chance of the correct diagnosis is in the top shade guesses. The x-axis is K from 1 to 10. Y-axis is accuracy. You can see AE's line is consistently above the PCP line across the entire range of K. This means AI was more likely to get the single top diagnosis right. K1, its broader list of possibilities. K2 to 10 was more accurate. The difference overall was statistically significant. P0,001. It confirms and effectively used both the conversation and the multimodal artifacts building on their previous text-only work, but now showing it works with actual image doc uploads too.
They did subgroup analysis too based on specialist ratings in figure 5b to understand why AMIE did better. First, the impact of image quality.
The left panel of 5TB looks at top 3 accuracy based on how specialists rated the artifact quality. When quality was low, accuracy dropped for both AMIE and PCPs as you'd expect, but AMIE's accuracy dropped less. It showed more robustness to poor quality images, suggesting it might be better at extracting useful info even from suboptimal data, which is a big deal for real-world telehealth.
And the middle panel of 5b looked at the impact of how well the artifact was used in reasoning.
Yes, this showed that when specialists felt the consultant AMIE or PCP used the visual data appropriately in their reasoning, diagnostic accuracy went up for both. This confirms two things. 1, the scenario successfully tested multimodal reasoning, and 2, effectively integrating visual data is important for getting the diagnosis right for both humans and AI. It also reinforces that AMIE's advantage wasn't just text analysis, it was genuinely using the image information effectively.
Page 20 shifts to the patient-centric evaluation, what the patient actors thought. Figures 50C and 11 show this. What were the main differences in their experiences?
The patient actors consistently rated AMIE higher on several aspects of communication quality. Things like politeness, listening, explaining things clearly, involving them in decisions, appearing honest and trustworthy. They also felt AMIE did a better job addressing their specific questions about the artifacts and explaining findings from them. Figure 5C left B0.01. They generally rated AMIE higher for addressing concerns, showing empathy, and making them feel their welfare was prioritized. While numerically higher, the differences for being happy to return or finding AMIE honest, trustworthy didn't quite reach statistical significance in that specific plot. But the overall trend was strongly in AMIE's favor.
Page 21 covers the specialist evaluation. Here, 18 specialists rated the consultations. Figure 5C aggregates this. So, your 6 breaks it down by specialty. What was the verdict from the experts?
The specialist views strongly echoed the patient action. They consistently rated AMIE's conversations higher overall across dermatology, cardiology, and general practice for all aspects of diagnosis, management, and history-taking quality. This was backed up by the MU scores. Specialists rated AMIE higher on interpreting artifacts. Reasoning with them and handling patient questions about them across all three fields, they found AMIE provided more appropriate diagnosement plans. Figure 6b significant. AMIE was also judged better at accurately interpreting artifacts, without hallucinating more often. Figure 6c significant. While top cake accuracy also trended higher for AMIE, figure 6a, it was only statistically significant for clinical documents, possibly due to sample size. Appendix D2 gives qualitative examples showing AMIE getting diagnosis right where PCPs didn't on the same case. Overall, specialists confirmed AI's strong multimodal handling, crucial for real-world use.
Page 22 introduces the automated evaluations complementing the OSCE. What were the two main aims here?
Two key things. First, to check the basic perception abilities of the base model, Gemini 2.2 Flash. Could it even see the relevant medical features in isolation, section 4.21. Second, to use simulations and auto-rating to quantify how much the state-aware reasoning framework actually improved performance compared to a simpler approach and how robust the system was. Section 4.22. It's about validating the design choices with automated metrics.
Page 23 digs into that first part. Base model provides necessary medical multimodal grounding. How did they check if Gemini 2.0 Flash could handle these medical artifacts?
They tested Gemini 2.0 Flash on standard benchmarks relevant to the OSCE tasks, seeing for skin images, PTBs XL, and ETQA for ECGs and clinical doc for clinical documents. They compared it to older Gemini versions too, figure 13 in the appendix. The results showed it was pretty robust, especially on skin images and clinical docs. Good at extracting features and processing info. ECGs were harder, which isn't surprising given their complexity, but it still showed gains over older models. So this gave them confidence that the base model had the necessary foundational perception skills across the modalities they needed, allowing them to build the more complex reasoning layers on top.
Page 24 presents the ablation study looking at the impact of state-aware reasoning. They compared AMIE to a baseline without this framework. What did this show?
This was critical to prove their special framework actually helped. They compared the full AMIE system to a vanilla version using the same base model but without the explicit state-aware phases and logic relying only on general instructions. They tested both using their automated simulation and auto-rating pipeline across the different domains skin docs ECGs. The results shown in Table 4 were clear. Adding the state-aware framework consistently boosted performance. Notably, diagnostic accuracy and information gathering scores went up significantly while hallucination rates stayed low. It strongly suggests that this structured state-aware approach is genuinely beneficial for this task. They also reference figure 14, which shows their auto-rater scores correlate well with human judgments, validating the automated metrics.
Page 25 introduces testing robustness with patient scenario augmentations. How did they vary the scenarios to test resilience?
They used LM to automatically tweak the original patient scenarios along 3 different lines or axes to see if AME could handle variations you might see in real patients. These axes were changing the patient's personality style, altering their demographics and making small semantic changes to their background story or symptoms that didn't change the actual diagnosis.
Page 26 gives more detail. Can you give examples of these augmentations?
Sure, for personality they might take a standard cooperative patient profile and make them sound more hesitant or maybe anxious using traits from psychological models. For demographics, they changed non-clinical things like age, gender, ethnicity to see if performance stayed consistent. And for semantic changes, they might slightly alter how it was described or change a minor detail in the patient's history, things that shouldn't change noses but might affect the conversation flow. They ran simulations with these augmented scenarios, and figure 15 shows the results. AMI's performance stayed really stable. No significant drops in accuracy. Info gathering or management quality, hallucinations staying low. It suggests AMI is pretty robust to these kinds of surface-level variations.
Page 27 looks at the impact of supervised fine-tuning SFT. Did fine-tuning Gemini 2.0 Flash specifically for this task improve things?
They tried it out. They fine-tuned the base model on synthetic dialogues containing text and images, skin ECG docs, and also on some modality-specific QA datasets. Then they compared this fine-tuned model to the original base model using their auto-rater. The results in figure 16 were mixed. SFT did significantly improve diagnostic accuracy for ECGs, but not really for skin images or documents. And interestingly, the quality of the conversation and particularly the management plan appropriateness for skin and ECGs actually seemed to decrease slightly. They suspect this might be because fine-tuning on a relatively small specialized dataset hurt some of the model's core language or instruction-following abilities. So given this lack of clear overall benefit, they decided to stick with the off-the-shelf-based model which offered more flexibility for their state-aware reasoning approach anyway.
Okay. Finally, pages 28 to 63 are Appendix D with qualitative results from the OSCE, including figures 17-23. What do these examples add?
The appendix adds crucial qualitative context. Section D1 has examples, figures 17 and 18, showing AMIE's internal thoughts along proside the actual chart, illustrating how it identifies knowledge gaps, uses artifacts to fill them, and updates its diagnosis. Section E.2 provides full dial 1923 for skin, document, and ECG cases, comparing AI's conversation with the PCP's conversation for the exact same patient scenario. This lets you directly compare how they handle the chat flow, request and interpret the multimodal data, explain things, and reason towards a diagnosis and plan. You can see instances where AMIE explicitly discusses the artifact findings and links them to the history, sometimes more clearly than the PCP example. It really brings the quantitative results to life.
Right? That detailed comparison is powerful. Okay, that wraps up our page-by-page journey. Let's try to summarize the absolute key takeaways from this deep dive.
Sure, I think the big things are first, the introduction of multimodal AME, a significant step beyond text-only diagnostic AI. Second, the novel state-aware framework using Gemini 2.0 Flash to dynamically integrate multimodal data is a key architectural contribution. Third, the rigorous evaluation using both automated methods and critically the expert-led multimodal OSCE. Fourth, the major finding that AMIE performs comparably or even superiorly to PCPs in these complex multimodal dialogues, particularly in diagnostic accuracy, management, reasoning, and empathy. And finally, the validation of its robustness and the base model's perceptual capabilities. And
what does this all mean for the future, particularly for data scientists like our listeners working in medical AI?
Well, it strongly suggests that AI has real potential to improve diagnostic conversations in telehealth by effectively using all available data, not just text. For data scientists, really highlights the value of thinking about system architectures that explicitly model the clinical reasoning process like this state-aware approach. It encourages moving towards systems that can flexibly integrate diverse data types, images, documents, maybe eventually sensor data within a natural dialogue. It's a blueprint for building more clinically grounded and potentially more impactful AI tools. Great summary. Thanks for walking us through the complex paper with such clarity. Hopefully, this deep dive has given you, our listeners, a solid grasp of this research and its significance. Yeah, it's definitely a paper worth digging into if you're in this space. It tackles some fundamental challenges in making AI truly useful in clinical practice.
So, our time together today has come to an end. We hope to see you again for the next podcast. Meanwhile, please like Linkfitty and subscribe if you want to be notified about the next exciting program.